Morning students. Last class we discussed about mechanical properties of fibers. For example, stress, strain, load, tenacity, load extension curve, work factor, work of rupture, all those things. In this class, we are going to discuss about the tensile properties of fibers. What is tensile properties? This table explains the tensile properties of fibers. So, tenacity and breaking extension. What is tenacity? The load applied to break the specimen and the linear density of the specimen. The difference, the ratio between the load applied and the linear density is called tenacity. Here, cm per tex. What is the breaking extension? The extension required to break the specimen is breaking extension. So, here the list of fibers. The cotton, strained Winston cotton has 45 tenacity cm per tex, the breaking extension of 6.8. The Bengal cotton has 19 tenacity and 5.6 breaking extension. Flax 54 tenacity and 3% breaking extension. Rami 59 tenacity, 3.7% of breaking extension. Silk 38 tenacity, 23.4 breaking extension. Nylon 47 tenacity, 26% of breaking extension. Viscose rayon in Flammond condition, we know what is Flammond. It is a continuous length of yarn. Indefinite length of yarn is called Flammond. So, viscose rayon Flammond has 18% of tenacity, 18 tenacity and 27.2% of breaking extension. Viscose rayon stable fiber, the limited length of fiber is called stable fiber. Here 21 tenacity and 15.7 breaking extension. Wool 14 tenacity and 42.9 breaking extension. The breaking extension is higher for wool fiber. Jute 31 tenacity and 1.8 breaking extension. Polyester 47 tenacity and 15% breaking extension. Acrylic 27 tenacity and 25% of breaking extension. Acetate rayon 13 cm per tex tenacity and 28.7% of breaking extension. These are the list of tensile properties of fibers. So, these values indicates that the tenacity of the fiber is more mean the breaking extension is less. So, in this diagram, the stress strain curve of textile fibers. So, how the fiber is behaving while applying the load. This is the stress strain curve of textile fibers. Here in this diagram, the y-axis we can take as specific stress cm per decitex or Newton per tex or gram per denier. In the x-axis we can take strain in percentage. So, in this diagram the fibers flax, rami, durafil, strained Winston cotton, uppers cotton, nylon, silk, fibro, viscose rayon, acetate rayon, wool and lanital. These are the fibers showing the stress strain properties. What is stress strain curve? When we apply load on the fiber, what is the value of strain? What is the stretchability? Whether the fiber withstand the load or if it extend is known as stress strain property of fibers. So, in this diagram, the flax, first we take this flax fiber. This is the flax fiber. So, the load 1 cm per decitick, 2 cm per decitick, 3 cm per decitick, 4 cm per decitick, 5 cm per decitick. These are the load applied. So, even we apply highest load, the flax fiber shows less elongation, this percentage, almost 3 to 4% of strain only. So, it withstand high load and the elongation percentage is very poor. So, if you applied more load for flax fiber means definitely it will lead to breaking point, but less percentage of elongation. The same rami fiber, next to flax fiber is a rami fiber. Rami also behaving like flax fiber. So while applying the highest load more than 5 cm per districts, the rami shows very good withstanding capacity of load. The elongation percentage is very less than 5%. But in case of wool, for example, we take it as wool fiber. This is wool fiber. So even we apply load less than 1 cm per districts, the elongation percentage is around 40 to 45% elongation. So if you apply small load, the wool gets maximum extension. That is the difference between the flax and a wool fiber. The flax fiber withstand up to more than 5 cm per districts. The elongation value, the strain value is around 4%. But the wool fiber, even less than applying 1 cm per districts, it shows more than 45% of strain. Then only it leads to breaking point. So in this, when comparing flax and wool fiber, the flax fiber withstands the highest load, but it has very less elongation. Here wool fiber, it withstands only slow or low level of load, but it extension, the strain percentage of wool is more. The same way the silk fiber. The diagram shows the behavior of silk fiber. So the silk fiber, when applied the load, at initial stage, the percentage of strain is more, around 10%. After increasing the load more than 2 cm per district, the withstanding capacity of silk fiber getting increased. So the silk fiber withstand heavy load up to 5 cm per district, even the strain percentage is 25%. But initial stage, the withstanding capacity is more. So after applying high load, it loses its withstanding capacity, the extension is heavy. This is the properties of silk fiber. Next, nylon fiber, it shows different curve. Initially the nylon fiber shows very good withstanding capacity up to 5 cm per districts. After that, sudden falling down its withstanding capacity, it increases its extension. So in nylon fiber, while applying up to 5 cm per district load, the elongation percentage is only 15%. But after applying more than 5 cm per district load, the elongation percentage increased up to 25 to 30%. So it withstand up to 5 cm per district load only. Same way the viscose rayon fiber. So initially it withstand the load. After the load crosses more than 1 cm per district, the elongation percentage gradually increased. So the viscose rayon withstand up to 1 cm per district load. After that, the strain is more even applying small load. This is the flumed viscose rayon. This is the stable fiber viscose rayon. Both are behaving same, almost same. Next, cotton. Here the cotton has two varieties, Stein Winston cotton and Uppers cotton. Normally the cotton fiber withstand the high load. In this diagram, even applying around 5 cm per district, the elongation percentage is only around 5%. Like bast fiber, cotton also withstand high load, the strain percentage of cotton is very less compared to other fibers. So these are the stress strain curve of textile fibers. What is stress strain curve? When applying load, the behavior of cotton fiber or behavior of nylon fiber, or behavior of flax fiber, behavior of wool fiber shows the withstanding capacity of the fiber while applying load. So what is the stress and strain percentage of a textile fibers is we can understand from the diagram. Okay. Next topic, humidity. What is humidity? The comfortable properties of fibers mainly based upon the absorbency properties of fibers. In the absorbency means the humidity value is the most important one. What is humidity? The amount of moisture present in the atmosphere is generally called as humidity. It depends upon the country to country or climate to climate or winter season or summer season. The humidity level in the atmosphere is getting vary. So depending upon the humidity present in the atmosphere, the absorbency capacity of textile fiber also different. So what is humidity? The amount of moisture present in the atmosphere is a humidity. Here the humidity has two parameters. First one is absolute humidity, second one is relative humidity, generally called as RH percentage. What is absolute humidity? The actual water vapor present in a air. The absolute humidity, the actual density of water vapor in the atmosphere. The actual water density present in a atmosphere is a absolute humidity. The unit is gram per cubic meter or cubic foot is the absolute humidity. What is relative humidity? It's a relative humidity generally called as RH value, RH percentage. The standard atmospheric condition is mainly based upon the RH value. What is standard atmospheric condition? 65% of RH and 20 degrees centigrade is the standard atmospheric condition. The standard atmospheric condition is normally followed in all the textile testing laboratories to test the samples. Then only we can get universally accepted results for testing the textile samples. What is RH or relative humidity? The ratio of actual vapor pressure to the saturated vapor pressure is the RH percentage. What is actual vapor pressure? The vapor present in the atmosphere, the vapor pressure present in the atmosphere with the saturated vapor pressure, saturation point. What is the value of vapor pressure and the actual vapor pressure, and it multiplied by 100 is the value of RH in percentage. What are the factors affecting regain of fibers? So first, what is regain value of fibers? Here there are two types, moisture content and moisture regain. Moisture content, a material has moisture means it has some moisture content. What is the value of moisture content? It is defined as the weight of water present in a material. For example, take a cotton fiber, to get the weight of the cotton fiber. So it shows some value. You dry the cotton fiber in a particular temperature. So the entire humidity present in the cotton fiber getting evaporated. So we can get only the value of cotton fiber. That removed or evaporated moisture is a moisture content of the particular fiber. So the amount of or weight of water present in a particular sample is a moisture content of the fiber. What is the formula of moisture content? Weight of water divided by total weight of material into 100. This is the moisture content formula. Moisture regain. So regaining. So what is regain? So when a sample is placed in a atmospheric condition, how much value of moisture regained by the fibers? For example, you place a normal fiber and you place a dried fiber. Two samples you place in the atmospheric condition. So the normal fiber which is present in the atmospheric condition still maintain the same weight. Suppose if you place the dried cotton sample. It observe moisture from the atmosphere. So it is called as Regen value of the fibers. What is the formula for Regen? Moisture Regen? Weight of water divided by oven dry weight of the material. What is oven dry weight? It's a 105 degree plus 3 or plus or minus 3 degrees centigrade is a oven dry weight of the sample. So you take a cotton fiber and you oven dry it around 105 degrees centigrade, then you weigh it, then you place the sample in a standard atmospheric condition. What is the weight of the sample? So the difference between these two is a moisture reagent. For example, cotton fiber, it absorbs more than 7% of moisture from the atmosphere. So the moisture reagent value of cotton fiber is 7%. The same way, the silk fiber absorbs more than 10 to 11% of moisture from the atmosphere. So the reagent value of the silk fiber is in standard atmospheric condition is 10 to 11%. For example, in polyester fiber, the moisture reagent value is only 0.4. Even though we place the sample in a standard atmospheric condition at very long time, the moisture reagent value of cotton is only, polyester is only 0.4. Factors affecting the reagent of the fibers. What are the factors affecting the moisture reagent of the fibers? So when a sample placed in a atmosphere or standard atmospheric condition, it loses or gains the moisture from the atmosphere. If a sample has saturated condition, so it loses its moisture to get equilibrium. Suppose if a sample is in a dry condition, it absorbs moisture from the atmosphere to reach the equilibrium condition. The reagent value of these factors, following factors affect the reagent value of fibers. The first one is RH value, time, temperature, history of the sample. RH value, how the RH affect the reagent value of the fibers. RH, normally, for example, cotton fiber, the standard reagent value of cotton fiber is 6 to 7%, not 65% RH value. But if the RH percentage is 20, if the RH percentage is 40, if it is 80, if it is 100, means the reagent value is gradually depends upon the RH percentage. For example, if it is 40% RH value, what is the reagent value of cotton means? Definitely it will be less than 6%, because the atmospheric temperature, atmospheric humidity is very low, so it absorb the reagent only less value than the standard one. The same way, the cotton fiber when present in a 80% RH atmospheric condition, the reagent value of cotton getting increased than the normal one. For example, normal cotton has the reagent value of 6 to 7%. If a sample is placed in a 80% RH atmospheric condition, means definitely the absorbency of cotton is increased more than 7% because of the RH present in the atmosphere. If it is 100, means definitely lot of changes happen in the cotton fiber. The reagent value getting increased. So depending upon the RH value on the atmosphere, the reagent value of the fiber getting improved or increased. Second, time. Time is an important factor for reagent value of fibers. For example, you place a dry cotton sample in your atmosphere. What happened? It absorbs moisture from the atmospheric condition. So when the time increases, the reagent value also increases. Suppose if you place a damp sample or wet sample in the atmospheric condition, what happens? The wet sample loses its temperature to get equilibrium. The attaining equilibrium is decided by the time factor. If you allow more time, it reaches the equilibrium. Temperature. So temperature is also one of the most important parameter for affecting the eigenvalue of fibers. If the temperature is high in the atmosphere or if the temperature is low in the atmosphere, definitely eigenvalue getting affected. For example, if the temperature is high means the eigenvalue of cotton is reduced. If the temperature is very less means the eigenvalue is somewhat improved. So the time and temperature is also most important factor for deciding the eigenvalue of fibers. The last one is history of the sample. The molecular or crystalline region or amorphous region or cross-linking agents or bonds, covalent bonds or what bonds present in the cotton fiber or particular fiber is the deciding factor for fixing the eigenvalue of the fibers. So based upon these four parameters, the eigenvalue of the fiber getting modified. This diagram shows the relationship between eigenvalue and relative humidity. How the eigen affects the and relative humidity correlates each other. So take sample A, sample B. Sample A is a dry sample. Sample B is a wet sample or saturated sample. So both sample placing in a same atmospheric condition. The dry sample absorb moisture from the atmosphere and reaches its equilibrium. The wet sample loses its moisture. It also attains the equilibrium condition. But even though both are same sample, the equilibrium condition of dry sample is not equal to equilibrium condition of wet sample. This phenomenon is known as hysteresis. So the eigenvalue or equilibrium condition of dry sample is less than the equilibrium condition of wet sample. Next important topic is moisture absorption behavior or properties of textile fibers. How the eigen and relative humidity affects the performance of fibers. So first we take this wool fiber. This is the curve of wool fiber. The eigenvalue of wool fiber is around 5 or 20% RH value. If it is 40, around 9%. If it is 60, around 11%. If it is 80, around 16%. If it is 100, it increases. The same way, the cotton fiber. Initially, the cotton fiber has less eigenvalue at 40%, around 7, around 4 value. If it is 60%, around it reaches around 7. At 80% of RH value, it reaches 10. If it is 100 means it reaches up to more than 20% of eigenvalue. So if the RH value increases, the eigen of the fiber also increases. It depends upon the type of fiber. For example, the terylene fiber, initially at 0 point, at 20% eigenvalue is around 1 less than 1%. After 40% of RH, it is also behave same. 60% also same. 80% is also same. Up to 100%, there is no change in the terylene fiber. After 100% of RH only, it gets little improved. The same way nylon fiber initial Regen value is around 2%. At 60% RH value it reaches around 4%. If it is 100%, the Regen value of nylon is more than 6%. So when the RH value increases, gradually it increases the Regen value of the fiber. The same way the viscose fiber, the viscose is behaving differently. The initial stage of the viscose fiber, when the RH increases, the Regen is getting increased. After 80% of RH, the viscose Regen value is more than the wool Regen value at more than 80% of RH value. So when the RH increases, the Regen value of the fiber also increases. So last paragraph we discussed about the relation between RH and Regen. The Regen increased based upon the relative humidity of the fiber. Thank you.